This is David Van Vranken here at UC Irvine, and this is our fifth lecture in Chemistry 51C in the Organic Chemistry series. This weekend, I was listening to a podcast by Daniela Bolelli called History on Fire, and the podcast was about this story by Xenophon, I think the Anabasis, talking about Xenophon's march of his I don't know what you'd call it, this renegade army that he hires to so that Cyrus the Great can go take over the kingship of Persia or something from his brother. But they mention in there, I'll just read the text. Xenophon's army finds this storage of honey that the Colchians had harvested. They just thought that honey's great, so why not have some? They eat it, and they start getting crazy sick, and the soldiers were running around and acting insane. It turns out, in this particular country, the honey can be extremely toxic during some particular part of the year. And if you eat it, you would get dizziness, hallucinations, and difficulty breathing. And that's interesting. And I've heard of this before. I think I mentioned it in a textbook that I wrote in chemical biology quite some time ago. And I thought this would be something that would be good to talk about here in our class in Chemistry 51C. So let's go ahead and talk about this honey. It turns out even nowadays you can buy this honey online. So here's an example from the website Etsy where you can order, it goes under the Turkish name Delibal, Turkish mad honey. I'm not sure why on earth anybody would buy this and voluntarily ingest it. They have all kinds of disclaimers on here, like adults only, and you assume full responsibility upon purchase. Why would you buy this stuff? It just seems kind of crazy to me. Let's go ahead and talk about maybe the biology, the physiology of these compounds. So where does mad honey come from? Mad honey comes from bees that get the nectar from some particular species of rhododendron plants. And those rhododendron plants, right, like Rhododendron ponticum that grow in Turkey in those areas where the Colchians were in 400 BCE, those rhododendrons produce a series of terpene compounds called grayanotoxins. And you can tell from the name that these are not particularly friendly compounds. Structurally, they're complex. These are well within the ability of synthetic organic chemists to synthesize nowadays. But these grayanotoxins are weak inhibitors of something called the voltage-gated sodium channel. And you have these variants of these voltage-gated sodium channels in all kinds of tissue, neuronal tissue, cardiac tissue. And unfortunately, the grayanotoxins are weak inhibitors of all of these voltage-gated sodium channels. They have no selectivity. They're going to hit the sodium channels that affect your heart rate, your brain function, your peripheral nervous system. Who would want to ingest something with such a non-selective compound? And as I was searching around the web to look for a good picture of the voltage-gated sodium channel, I found an article that was published in Science by some Genentech authors in collaboration with some other groups where they had shown, and this is very typical of what happens in medicinal chemistry, is once you find a molecule in nature that can block a channel or target some protein, then you send the medicinal chemists after that to go design better, more potent compounds. And over here, GX938 is one of the synthetic compounds they made. It's over 10,000 times more potent than grayanotoxin, and it is selective for the channels that would be associated with a single disease state. So really interesting kind of historical phenomenon where people, I guess these Colchians, realized they could trick the Xenophon's army into eating this poison honey, this mad honey stuff. But interesting to talk about this and how medicinal chemists often get leads for pharmaceuticals. All right, let's go ahead and talk about our lecture here for today. We finished chapter 18 in the Gorzynski-Smith 5th edition textbook, talking about electrophilic aromatic substitution. You guys need to be working problems like crazy. Try to finish them before they're due, I think, this Thursday. Today, we're going to go talk about another chapter about carboxylic acids and phenols. And really this chapter is mostly about the acidity of OH compounds like carboxylic acids and phenols. So let's go ahead and talk about acidity of OH compounds. So in our textbook, there's an appendix that talks about carboxylic acids or all different types of functional groups and their acidities. And one of the unfortunate things is that we're going to be using pKa's as a guide to acidity. I expect you to know all the pKa's on this page, and I expect you to know the pKa's for all the common functional groups as we cover them in this chapter. So this chapter here is about OH-containing compounds. So I expect all of you to know that alcohols and water have pKa's around 16. So whether it's an alcohol side chain of the amino acid serine or threonine, or just ethanol or methanol or water, the pKa's are around 16. We don't need to worry about if it's 15.8 or 16.2 or 17.1. Those are small differences that we're not worried about. But when we compare regular aliphatic alcohols like methanol, ethanol, butanol to phenols, where there's a benzene ring directly attached to that OH compound, those are 1,000,000 times more acidic. They're 10 to the 6 more acidic. They're 6 log orders more acidic than regular alcohols. Remember, pK is a logarithmic scale, so a difference of 6 doesn't look like much, but 10 to the 6, if you're counting dollars, that means a lot. And finally, we get to carboxylic acids, right? That's way more acidic than water or any alcohol. That's 11 orders of magnitude more acidic. So let's go ahead and draw this out, the relative acidity versus water. You all need to know that the pK of water is 16. So I'm going to assign that a relative acidity of 1. And so if I think about it on a log scale, phenols are 10 to the 6 more acidic. Let's write that out, right? Most people don't have an intuitive understanding or appreciation of logs, but we understand regular base 10 numerals, 1,000,000 times more. When I write it out with zeros, you get a sense phenols are way more acidic than regular alcohols or water. And carboxylic acids, see, now we're talking 11 orders of magnitude more acidic. I hope I'm counting my zeros correctly in the commas, but I think that's 100 billion times more acidic, or 10 to the 11. Wow, carboxylic acids, it's so much easier for them to donate a proton. I guess that's why they're called acids. Finally, we get down to acids like toluene sulfonic acid. You learned about tosyl chloride when we way back in those chapters earlier in the Chem 51 organic chemistry series, where tosylate was used as a leaving group. And later on in this quarter, we're going to be using toluene sulfonic acid, which you can make through electrophilic aromatic substitution. It's a common organic acid that we use in organic synthesis. And now the pK for this is in the negative range. So relative to water, it's, I'm not really good at math, but something like 23 orders of magnitude more acidic. I'm not even sure if I can write the right number of zeros. 1, 2, 3, 4, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. There we go. I'm not going to even try to put the commas in there. I'm going to end up messing up. The point is that pKa's may not look very different because they're log scale, but when you write them out with the zeros, we're talking about massive differences in acidity. And the goal for chapter 19, a major goal, is to try to understand how could we have predicted, what tools do we have to think about why some OH compounds are very acidic and why other ones are not. And toluene sulfonic acid, sulfuric acid, is about 100 times more acidic than benzene sulfonic acid or toluene sulfonic acid. I'm not going to write all the zeros out. You can do that on your own. But it's way, 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 way more acidic than water. And as you remember from our recipes for electrophilic aromatic substitution, when we want a really powerful acid to drive nitration or sulfonation of benzene rings, we use sulfuric acid for that. All right, this book seems to always introduce functional group chapters by talking about IUPAC nomenclature. And let me just be clear, I don't ask IUPAC nomenclature on my exams. I don't think that's a useful way for us to spend our time. But I would note that when you look at versions of the dental exam, the MCAT for entrance to medical school, or health schools, for some reason they ask you IUPAC nomenclature. Organic chemists use a program called ChemDraw. We draw the structures in and hit a button and it tells us the name of the compound. So what do I really expect you to know when it comes to nomenclature? Well, I expect you to know the names of functional groups is what I expect you to know. So let me go ahead and draw out, for example, let me change to black because I love the high contrast of black. So if I draw probably one of the simplest of carboxylic acids, certainly the most common, that would be acetic acid. And that's not the IUPAC nomenclature for this, but it's been used so long that we tend to use acetic acid. Obviously this is a 2-carbon acid, so I think the IUPAC name is ethanoic acid. Nobody calls it that. It's acetic acid is the common name. So if I want to think about where I would find acetic acid, you don't see it that often written down somewhere. This is what you buy as vinegar in the grocery store. Vinegar is a 5% solution of acetic acid in water. What you more commonly find is not carboxylic acids when you look at food packages and things like that. What you find is deprotonated versions of carboxylic acid. So let me go ahead and draw out the deprotonated version. I'll just draw out this acid-base equilibrium, where if you took a bottle of acetic acid and treated it with an equivalent of sodium hydroxide, you would get the negatively charged version, the conjugate base derived from that acetic acid. And then, of course, you get water, but that's not that interesting of a part of this equilibrium, but it's part of it. And we have a special way to describe these deprotonated versions of oxygen-containing compounds, or deprotonated versions, anionic versions. Conjugate bases of organic molecules will always end in the word ate. They have that suffix ate on there, which is quite useful to see that on there. Let me go ahead and write out the name for this. This would be referred to as sodium acetate, not acetic acid, but sodium acetate. So the first part of that name is the positive counterion, the cation, and then we just replace acetic acid with acetate. So as soon as I hear this suffix ate, I know that there's a negative charge on there. Something got deprotonated. So when you look at food packages, which I always do, you'll find carboxylic acids that have been deprotonated in a lot of the food things. Why would people do that? Because carboxylate salts, the salts tend to be water soluble. So let's go ahead and take a look at, if I just take a common package of chips or crisps in the UK, what would I see there? Well, I would see sodium acetate as an ingredient in there. But I also see a lot of other deprotonated molecules in there. Monosodium glutamate. That's the neurotransmitter glutamic acid, and one of the 20 ribosomally incorporated amino acids is glutamic acid. They're throwing a monosodium salt in there. Malic acid they're throwing in is the protonated acid. Citric acid they're throwing in there. Anything that's a carboxylic acid will taste sour and refreshing to the human palate. But there's other anionic stuff in there. I can readily see sodium caseinate. That's the milk protein casein. They've treated it with base to convert it into anion. Disodium guanylate is one of the RNA bases. I don't know why they're throwing that in there. I guess it tastes good or something. But look for that word ate when you look at food packages or any listing of organic molecules. That tells you that there was some sort of organic molecule, usually it's organic, that was deprotonated, usually to make it water soluble. So carboxylic acids with the proton on there taste sour and refreshing, but again, it's always a lot easier to have water soluble versions that are deprotonated. Things with charges tend to be water soluble. Okay, in this chapter, so again, I don't expect you to know IUPAC nomenclature. Well, it would be great if you could take the extra time on your own to learn that, but I'm not going to test you on IUPAC nomenclature questions. I'd rather you understood chemical reactivity and organic transformations. I do expect you to know spectroscopy, and on every exam I've got a spectroscopy question, at least one, usually one on the regular exams, because that's a powerful tool and a part of organic chemistry. And they expect you to know that for those standardized exams. So how would you know if you have a carboxylic acid on your molecule if you were using spectroscopy? Probably the most reliable way to identify whether you have a carboxylic acid is to look at the proton NMR. And past 10 parts per million. Not a lot of stuff shows up there. What you see out here past 10 parts per million are acidic protons, and about the only acidic one that's really acidic enough would be a carboxylic acid. So what you'll find is that if you've got a carboxylic acid, you'll see some broad lump that integrates for one proton. Sometimes it's so broad that you have to really zoom in to see that there's this hill, this slight hill there. But exchangeable protons, hydrogen bonding protons tend to be broadened, and these appear past 12 ppm. Where does it occur exactly? Well, it depends on the concentration, unfortunately. The concentration affects how much hydrogen bonding there is in the solution. So there's a concentration-dependent chemical shift. But past 10 ppm broadened, that's a carboxylic acid. Now, there's another spectroscopic technique that you can use to provide evidence that there's an exchangeable OH in there, or NH. Exchangeable hydrogen bonding protons, like OHs and NHs, give broad lumps. And the more acidic they are, the better they are at hydrogen bonding. In other words, the bigger the lump is going to be. And the biggest lumps that you see out here in this region are carboxylic acids. So if you've got an alcohol, you can have a big lump, or some NHs at high concentration can give a big lump. But really the biggest lumps, just one OH. And what are you seeing? You're seeing this stretch of the OH bond, an acidic OH stretch. And the more it's hydrogen bonded to other stuff, the more lumpier it is because it appears at all different frequencies. So an OH stretch will often give you this just huge lump that takes over the whole spectrum. That tells you it was kind of a concentrated sample. But right, that one OH bond can be as mountainous, as big as like 30 CH bonds. The CH bonds don't give as big of a signal as a polar OH bond. Okay, what about that carbonyl? So C13 spectroscopy is actually used for telling you that there's a carbonyl. So if you have carbonyls with heteroatoms attached, like carboxylic acids, acid chlorides, amides, esters, if there's a carbonyl with either oxygen, halogen, nitrogen attached to it, you're going to get these carbon-13 peaks that are somewhere in this region of about 165 to maybe about 185 or maybe 190. So let me give you a range of about 155 to 190 parts per million. Anything higher than that is probably an aldehyde or ketone. But in that range, that's where unfortunately, esters and amides are really common. So it doesn't do a lot of good to narrow it down and say, well, it's either an ester or an amide or carboxylic acid, because you really want to know, do I have an ester or do I have a carboxylic acid? And that's why proton and NMR and IR could be more diagnostic when used in combination with C13. Okay, so there's this big lump region here. That's like, let me just give you some numbers there, around 3,500 to, it can be so lumpy that it extends down to 2,500, but it's mostly in that in the mid 3,000s range. It would have to be really lumpy to extend all the way to 2,500. And then this 10 to 12 ppm region and broadened. Let me just say broadened for for proton NMR. So 10 to 12 ppm broadened in proton NMR. All right, let's go ahead and talk about what kinds of things would stabilize an oxygen anion. Boy, pKs are so hard to work with. I try to make this comment here that pKs are not user-friendly. Invariably, as a synthetic organic chemist, I'm usually interested in how much carboxylate or anion do I have in my solution, not how much carboxylic acid. But all we've got are pKs. Why is that? We have tables and tables and tables and tables of pKs from 200 years of chemical work, because titrations are easy to do in the laboratory. You've probably done titrations with an indicator yourself in high school or grade school. So we have lots and lots of pKas. What we don't have are tables of anion stability, which is the converse of acidity. So the thing you have to remember is that when you have a lower pKa, that means that the H has higher acidity. So what we're going to find is that we're more interested typically in the conjugate base. We're not all that interested in the acid form. We're usually interested in the nucleophilic form, the conjugate base in Chem 51C. But all I have to tell me about whether the conjugate base is stable or unstable is pKs from acidity. So again, we've got tables and tables that tell us how acidic something is, and you're supposed to use those pKa values, those tables, or the pKa values that you memorize to tell you which has the most stable conjugate base. So some things tend to be very acidic, and that means low pKa, if and only if the conjugate base is very stable. So I'll just write if and only if. So we're often going to be interested in the stability of the anion, but all we have to tell us about that is the conjugate base. So there's this kind of thinking that you need. So here's two different carboxylic acids. Let me just remind you of the pKs. I told you, you need to memorize the tables from that first page of pKs. Those are common functional groups. You need to know that the pK of organic alcohols is around 16. You need to know that the pK of carboxylic acids is around 5. And right, one of those is more acidic than the other. The one that's more acidic is the carboxylic acid. And how much more acidic? 11 log orders more acidic. So 10 to the 11 more acidic. Wow, that acetic acid is way more acidic than just a regular alcohol. Now, why is it? We're going to get some practice with this. Why is it that that's more acidic? The way you judge the acidity of OH compounds is you draw the conjugate base. So let me go ahead and switch back to my high contrast black pen here. Let's go ahead and draw the conjugate base and try to decide, when we look at this, which of these is more stabilized. That's how we're going to determine which of these, or try to understand which is more acidic. So when I draw these two, I don't know why I drew the lone pair on the ethoxide, or maybe I'll draw it over here on the acetate anion. So one of these is way more stable. Which one is more stable? Well, the one that has the opportunity to resonance stabilize that anion. So let me go ahead and just draw that resonance stabilized anion here. The carbonyl provides the opportunity for resonance stabilization here in this acetate anion. So the acetate anion is way more stable than the ethoxide anion, which has nothing to stabilize that negative charge on the ethoxide. So that's why acetate is more stable. It has resonance stabilization, 10 to the 11 orders of magnitude more stability. And that makes the acetic acid more willing to give up its proton because it can form a conjugate base that is more stabilized. So just remember that this resonance stabilization, let me just change it to a different pen color here for dramatic effect. So this is resonance stabilized. And I've got two different resonance structures, and in both cases, the negative charge gets to be on an electronegative oxygen atom. So if all your resonance structures put negative charges on electronegative atoms, it's going to be a really stable anion. So look for that. Okay, so what are some of the types of questions that arise in this chapter? So one of the types of questions would be, okay, if you compare two 6-membered ring compounds that have the same number of carbon atoms, the only difference is the number of double bonds. So here we're going to compare a phenol to just an aliphatic alcohol. Let me just remind you of the pK difference here. The pK for just a regular aliphatic alcohol is around 16. It's a little bit higher, but we don't care whether it's 17 or 16. We don't have any reason for us to, or any business memorizing that this quarter. So we'll just say that all organic alcohols have pKs around 16. Phenol, though, is not just a regular organic alcohol. It's got a phenyl group attached. And the pKas for phenol are around 10, so 1,000,000 times more acidic. If we want to understand the relative acidities of these, why is the phenol 1,000,000 times more acidic? We have to draw out the Lewis structures for the conjugate base. So let's just automatically, if somebody asks you to think about the relative acidity, you just automatically ought to draw out the conjugate base. And that takes some effort, right? Look at all the work we have to do drawing these conjugate bases out. In other words, what would you get in the acid-base reaction if you deprotonated these? Well, the cyclohexanol conjugate base, the alkoxide, has nothing to stabilize that O minus. There's nothing. That's why it's got the same pK as water and methanol. But when we come over here and we look at the phenoxide anion, we can donate these electrons through resonance. So let's go ahead and draw out some of these resonance structures that we can draw here. I'm going to draw a number of different resonance structures. Let me start here. And notice how I'm ending my arrow super carefully here. I'm ending my arrow super carefully on an atom. I'm not ending my arrow on the bond. Right? That's perfectly fine, but I'm trying to get you used to the Sapling online homework system, which is what we're using for our homeworks. And this quarter, I'm telling you, if you do any curved arrow pushing on Sapling for my problem sets or for my exams, I want you to do all the arrow pushing in one way, which is to make your arrows end on atoms and not in the middle of bonds. And the reason why is that way there's fewer possible answers to the questions. Okay, so I can't make a fifth bond to this carbon. I better break one of the bonds to that carbon atom if I'm donating electrons in. So I'm going to choose to lift up this pi bond here, and I'll make that those electrons just sit there on that ortho position. Let's go ahead and draw out the first of several resonance structures here. According to my arrow pushing, I'm going to make a CO double bond. So let me draw that in. There it is. And according to my arrow pushing over here, I just broke that double bond. So let me make sure that double bond's broken and the electrons are now given to this carbon at the ortho position. And the other double bonds didn't change. So this is one of my resonance structures, but I've got more resonance structures that I can draw. So I can draw another resonance structure where I take these electrons and add them to this carbon and then give these electrons to this carbon over at the end. So here's yet another resonance structure that I can draw. And so I'm going to keep that carbonyl there. There's the carbonyl. And now the lone pair is para to that oxygen substituent. Sometimes I circle my charges to make it more obvious. I'm just going to circle that. So, and so again, sometimes I circle them, sometimes I don't. It's just I'm worried if you aren't going to see that that's a negative charge. I oftentimes circle that for emphasis. But there's no rule about do you have to circle your charges or not. All right, we've got one more resonance structure that we can draw. Boy, all these resonance structures here. I'm going to make the arrow, the curved arrow, end on the atom, not in the middle of the bond. And I'll pick up, if I make a fifth bond to this carbon, I have to break a bond. There we go. So let me go ahead and depict it like that. And I'm going to draw my last possible resonance structure, which is going to put a negative charge on that bottom carbon. So there's 3 additional resonance structures I can draw for the phenolate anion as opposed to the cyclohexanolate. I'm not even sure that the correct way to describe this is there's 8 anion derived from cyclohexanol. Phenols have all this resonance. Now, it's not as good as a carboxylic acid because there is, with these 3 extra resonance structures, none of these 3 extra resonance structures put the negative charge on an electronegative atom like oxygen. And that was possible with carboxylates, but just phenolate anions, all my negative charges on my resonance structures are on carbon, which is not as good. And that's why you only get a millionfold more stable as the oxygen anion as opposed to a carboxylate anion, where I just had one resonance structure, but that other resonance structure put the negative charge on oxygen. So you get lots of resonance here. So at least you get a millionfold increase in acidity by having this benzene ring next to the OH group, because when you look at the conjugate base, you can see all that resonance in there. And you need to be able to draw these resonance structures. It can be more subtle than this. Let's go ahead and compare the acidity. This to me looks exactly like the kinds of questions they ask on the MCAT or the DAT, where they expect you to know how to think about resonance and arrow pushing and map it onto pKa's, which are these mind-bending things where lower pKa means higher acidity. So it seems like they love to trick you with that. So if I ask you to compare these 2 different phenols, they both have OHs attached to benzene rings, but one of them has a nitro group ortho to the phenol. And this now makes it about 1,000 times more acidic. So if I look at the pKa's for these 2 compounds, the pK of the phenol is about 10. The pK of the ortho nitrophenol is about 7. It's about 1,000 times more acidic. Lower pK means higher acidity. So if we want to understand this, the first thing we have to do is draw out the conjugate base. In other words, if we deprotonate it, what kind of resonance do we have there, or what kinds of effects will stabilize this? Let me go ahead and draw out the resonance structure for the nitrophenolate, the nitrophenol conjugate base. Okay, so these are the two anions. So if the nitrophenolate anion, if nitrophenol is 1,000 times more acidic, this nitro group must have some stabilizing effect on this O minus. There must be some stabilizing effect. So let's go and draw out some of the resonance structures. And in order to do this, we're really going to have to draw out the Lewis depiction of that nitro group. So let's get ready to draw 4 resonance structures here at the bottom of the page. And I'm going to draw this, maybe I better start off by drawing maybe the best resonance structure. I'm going to take these electrons here in the oxygen, and I'm going to donate them into this carbon, and I'm going to have to break one of the bonds to this carbon atom if I do that. So I'll break the pi bond, and I'll give the electrons to that carbon right next to the nitro group. And there it is. Let me go ahead and draw that resonance structure. And if that nitro group has an effect, and kind of makes sense, the first resonance structure I go after here is going to be the one where the negative charge is right next to that nitro group. And let me go ahead and draw out the resonance structure for that nitro group. Here's one of the resonance structures where I put the negative charge on the top oxygen. You might have been just writing NO2, but you have to be used to drawing out the Lewis depiction for that nitro group resonance structure. So this is the, and look at all these charges. Doesn't that look confusing? You might think, that's wacko. How can there be 2 minuses and a plus? That's just the way it's depicted. A nitro group, you cannot draw a nitro functional group without having charges, formal charges on some of the atoms. So immediately I can tell, there's some resonance structures that I can draw here. And I'm not going to draw the initial arrow pushing, but this nitrophenol has a lot of the same resonance structures as I was able to draw for the phenolate anion, where I could move this negative charge around the benzene ring and place it on different carbons. But these are not really interesting resonance structures. They're just like the resonance structures that I drew for the phenolate anion. So I'm not going to really draw the arrow pushing here for this. I'm just going to make it clear that, yeah, these are the same resonance structures I drew previously for just regular phenol, for regular phenolate anion. That's kind of boring. The resonance that's really cool here, the one that really explains stabilization of this phenolate anion by the nitro group, is the one where I push the electrons over here onto the nitro functional group. Now I don't want to make a 5th bond to nitrogen, so I'm going to break one of the bonds. And there we go. I'll give the electrons to the oxygen. So now when I draw this, I can see that in this resonance structure, I'm running out of room here, so I want to make sure I don't run out of room. I'm going to end up with the negative charge on oxygens. All the negative charges here in this resonance structure end up on electronegative atoms, on oxygen atoms. That's good. That's a great resonance structure. It's better than, this is the best resonance structure of all these resonance structures. So let me go ahead and make a point of that, because that's, so, this resonance structure is super special because it puts negative charge on oxygens, and oxygens are an electronegative atom, on oxygens. I mean, the only thing better than oxygen is fluorine, and there's no fluorine in this molecule. So, wow. Okay, so that's why the nitrophenol is 1,000 times is more stable when you deprotonate it than phenol, because we have extra resonance that for nitrophenol that we just don't have for the regular phenol. So that's a particularly good resonance structure. You're getting down to the point now where, because the pK is 7, you might remember from the Henderson-Hasselbalch equation from freshman general chemistry that if the pK is 7, that means half of it is protonated and half of it is deprotonated in a buffered solution that's pH 7, like inside your cells or serum or the cytosol of cells. Okay, resonance is the big stabilizer of oxygen anions. That's the big gorilla in the room there. I'm skipping section, I'm not covering section 19.7 in the Gorzynski-Smith 5th edition. It's a review of ways to synthesize carboxylic acids. And really the the two main ways to synthesize carboxylic acids that you covered in chapter 12 on reduction and oxidation were chromium reagents like potassium dichromate and sulfuric acid, which is something you apply to primary alcohols. And you should practice those. You might have forgotten those from chapter 12, but when you work the problems on sapling and in the textbook, it'll force you to go back and remember, oh yeah, if I take primary alcohols, I can convert them to carboxylic acids. And then there's an ozonolysis reaction that you can do with an oxidative workup condition. It's not very common. Really. Okay, so let's go ahead and take a look at another kind of effect that can stabilize anions, but not as much as resonance. And the book refers to these as inductive effects. Some books will refer to them as polar effects, but they're not. And unfortunately, the book tends to really focus on these, even though it's not as big of an effect as resonance stabilization. But it is an effect. So here's an example. When we take the most electronegative atom we can think of, which is a fluorine atom, when you put the substituent next on the carbon atom that's next to the carbonyl, you can see 100-fold increase in acidity. What that means is if fluoroacetic acid is 2 log orders more acidic than acetic acid, this fluorine atom must be giving some stabilizing effect to the conjugate base. And what is that stabilizing effect? You can kind of think of it as a Coulombic effect. Coulomb's law, 2 charges, right? The pluses and minuses are kind of a good thing. And there's so many protons in the nucleus of fluorine. And so, so I don't know what I'm trying to represent here by writing delta plus. What I'm trying to indicate is there's lots of protons in the nucleus of fluorine. It's very electronegative. I'm not sure if delta plus is the right symbol here, but fluorine is so electronegative. Sometimes people draw things like this to indicate a polar effect or this kind of, but having so many protons in the nucleus of fluorine is what makes it electronegative. It's about the same size as carbon, nitrogen, and oxygen. And so having all those protons nearby, an O minus, helps that to stabilize the oxygen. Let's go ahead and take a look for fluorines aren't very common. Certainly not in natural biological molecules, they're not common. But let's take a look at what happens when we put a chlorine atom, which is not as electronegative as a fluorine atom, on carbon. Oh, I'll have to think about this. I hope I'm using the pK for the. I'm getting a little bit worried that I might have used the pK for the chloroacetic acid. The important point here is that when we put a chlorine atom even one further away, so the pK of this molecule I'm sure of is 4.0. And if I have this chlorine 3 atoms away, now the pK is so close to the pK for acetic acid, it's almost like the chlorine is not even there. 0.3 log units is so minuscule and so small, that's not even a factor of 2 different instability. So the further and further that electronegative atom is away from the carboxylate anion, the less of a stabilizing effect you're going to see. Here we've got 3 chlorines. I'm beginning to worry that maybe I misdrew this and maybe it was supposed to be chlorine on there. I'll have to find out what is the case, what was the right, whether this was the pK for chloroacetic acid. But when you have 3 chlorines on here, the effects are almost additive, but not quite. So now it becomes really quite acidic. Nothing like sulfuric acid, though. So now the pK is 0.9. So if you have 3 chlorines, you get more of an effect. When you move the chlorine farther away, you have less of an effect. Here's another atom that actually has a formal positive charge, not just lots of protons in the nucleus, but a formal positive charge. This is glycine. It's the protonated version of glycine. And this has a pKa of about 2 orders of magnitude more acidic. The OH is more acidic. So in other words, if you've got a negative on one charge, a positively charged ammonium group on the other side of the molecule would help to stabilize glycine as the Switter ion, where there's a plus and a minus on there. All right, so anything that stabilizes the O minus form of an OH compound is going to make it, the OH compound, more acidic. It affects the equilibrium, and pK is an equilibrium effect. Now, one of the tough things that we have to deal with, and we're going to see this in a couple of chapters, in chapter 22, is we're going to find out that carboxylic acids can actually act as bases. If you put in an acid that is so strong, and the strongest one we can think of here is sulfuric acid, the strongest acid that we can think of here. This sulfuric acid has a pK of -9. This is -9, not 9, but -9. It is such a powerful acid that it will actually stick a proton on the carboxylic acid. That's going to turn out to be useful chemically when we get to chapter 22. So, the carbonyl lone pair has a lone pair on the oxygen that can be protonated. So let's go ahead and draw out these species. This time I'll draw out the Lewis structure for sulfuric acid because we don't do that often enough. Here we go. There's the Lewis structure of this bisulfate counterion. And what you get out of this is the protonated version of acetic acid. This is going to be an important intermediate in a few chapters. So this may seem weird to you, but yes, acetic carboxylic acids can act as bases if you've got a powerful enough acid. And the equilibrium here, of course, now it really wants to get rid of that proton. This species here has a pK of -6, so it's not as, this protonated carboxylic acid is not as, so -6. It's not as acidic as the sulfuric acid, but it is acidic. And this still has resonance stabilization in here. There's a resonance structure that I can draw. Let me go ahead and use arrow pushing here to go from one resonance structure to another. So it may freak you out to see that proton sitting there on that carboxylic acid, but it's still resonance stabilized. It's not like the positive charge is stuck on just one atom, right? It sucks to have a positive charge on oxygen, but at least it's distributed onto two different oxygen atoms. So that's a resonance stabilized, I guess you would call that the protonated form of the carboxylic acid. I want to make one point here. When in a couple of chapters I tell you to protonate the carboxylic acid, I just want to remind you that whenever you have a carboxylic acid, don't ever stick the proton on these electrons. Okay, let me tell you, when should you protonate that? Never. Don't ever protonate what's called the carboxylate, the carboxylate group. Never protonate this group right here, this oxygen atom. It's the carbonyl oxygen that you protonate. And the reason you would never protonate that is you would end up with a resonance structure. If you did protonate that, you'd end up with a resonance structure that would look like this. It would just be horrible. So don't ever draw anything like this. You have no way to generate anything that looks like this. I could certainly draw it on paper, but that just looks hideous. And as soon as I draw our most important resonance structure for carbonyl groups, this will become more important in the next chapter, right? The most important resonance structure that we can draw for a carbonyl group puts plus on the carbonyl carbon and minus on the carbonyl oxygen. When you see two pluses right next to each other on neighboring atoms, boy, I showed you one mechanism with nitric acid and nitration where there were positive charges next to each other. I told you, don't ever do that again. So hope this makes you uncomfortable to see positive charges on neighboring atoms. It's the positive charge on neighboring atoms right next to each other that's really uncomfortable. So get ready, you're going to see more of this protonation of carbonyl groups in chapters 21, especially chapter 22, we'll be seeing protonation of carboxylic acids. Okay, that's us for today. So we have an exam in 1 week. So work the problems in the textbook, get practice problem solving, work the problems in the sapling homeworks. Just get every opportunity, use every opportunity you can to practice solving problems. The exam from 51C, our exams are posted in the files on the Canvas webpage. And they're the paper versions, and we'll be putting up on Sapling some sample exam questions for you to practice on so you can see the format. So there won't be any surprises there. And they should be formatted just like your homework. So I tried to redo all the Sapling problem sets so that the problems and the problem sets are formatted so that they don't use a different set of rules that we use for the exams. All right, I will see you guys on Wednesday. And thanks for coming here to my lecture.